Remember I said that our interest in this class is on how we can apply the scientific method to understanding the world, right? So how specifically might we use the scientific method when we're talking about lumosity? Well, before we get there, we have to understand what the heck science is and what the scientific method is, right? What makes an idea even scientific, right? I mean, science always starts with an idea. Where do those ideas come from? I mean, these ideas can come from carefully researched data, extending other people's ideas. Certainly, that's kind of the classic idea where science gets their ideas. But science actually doesn't care where the idea comes from. And science ideas can come from anywhere. They can come from in your head and having a vision, right? They can come from a spontaneous eureka moment. They can come from any source, right? That's the key. Where these ideas come from doesn't matter. What makes an idea scientific is not its source, but what it's able to do, right? So, for example, somebody wheels a piano up to the top of the building and pushes the piano off the building, and here we go. We're looking at this paused in time. What's going to happen to this piano? Is it going to stay suspended in the air, floating there? Is it going to suddenly take off and go into orbit, right? Is it going to return to the platform? Or what's it going to do? Yeah, it's probably going to smash down on the sidewalk, right? Why? Why is the piano going to do that? Right? Well, we have this understanding of gravity and the pull of gravity. Right? What we just demonstrated here was some important elements of the scientific idea. Right? The scientific idea can form a hypothesis. The hypothesis is what we think is going to happen next. Once we set up our circumstance, what's going to happen, right? And it has to be a testable prediction. And the hypothesis is going to give us something that we can see, that we can test, that we can measure. And it's going to be consistent with our theories of the world, right? Our theory is a set of principles and observations that kind of formulate our understanding of the world, right? The hypothesis in this case was that the piano was going to fall down and smash on the sidewalk. The why is the theory of gravity, right? This is an important distinction. A hypothesis is fundamentally different from a theory. A hypothesis often comes from a theory, right? But a hypothesis is not just the prior step before theory, right? A hypothesis is not going to graduate to become a theory if it has enough evidence or if it's proven correct, or one of these other things. Sometimes students have this misconception that ideas start, as a hypothesis, then become a theory, then become a law, or some other progression. That's not how it works in science. In science, a hypothesis is a specific thing, a specific testable prediction. A theory is a collection of principles and observations that help us understand the world, right? These are two different things, right? Now, oftentimes our hypothesis comes from our theories, right? But hypothesis will never become a theory, right? So again, the true key here, right? As we said, science starts with an idea. What differentiates scientific ideas from other kinds of ideas is their ability to form specific, testable predictions. Okay? And what allows us to do that, one of the key properties of what makes something a scientific idea is what we call falsification, or that it is falsifiable. In other words, an idea must be provably wrong for it to be scientific. If an idea cannot be proven wrong, that doesn't mean that it's a wrong idea. It simply means that it is not a scientific idea. Now remember the spheres of knowledge that we talked about. And let's go to the sphere of art, for example. Is a particular painting a beautiful painting? Is there a way to prove that that painting is not beautiful? Right? If our hypothesis is that Monet produces beautiful paintings, can we prove that wrong? Right? Well, beauty is often in the eye of the beholder. For some people it might be, for others it might not be. It's not really an idea that can be proven wrong. It's not an idea that is falsifiable. Right? We run into this with religious ideas all the time, right? We ask questions about the existence of God, about the nature of the meaning and purpose of life. These things by their very nature are not cannot be proven wrong. They're not falsifiable. right? And the very act of not being falsifiable means that they are no longer within the realm of science. They are not a scientific idea. It doesn't mean that the idea is wrong. It doesn't mean that the question is invalid. It doesn't mean that it isn't an interesting thing to talk about. It means that science can no longer be applied to it. Falsification is the key. Right? Once we have an idea that is falsifiable, that means it is testable. Since we can prove it wrong, we go out there and we try to prove it wrong. We formulate our hypothesis. This is what we're going to think has happened. And then we go out there and we try to prove ourselves wrong, right? This is the gather our data stage, right? Of the scientific method. We go out there, have a specific testable prediction, and we attempt to prove us wrong. Once we collect our data, on our observations, on our measurements, we pull them back and we see, did they match our hypothesis? Did they match our expectation? Okay. If it doesn't, we have to go back and reevaluate the hypothesis. We have to say, okay, my hypothesis was wrong. I proved my hypothesis wrong. What happens if the data does match expectation? Well, we're not done yet. Now we should be in the realm of replication. We should do the whole thing all over again. We can do it with slight modifications, with slightly different questions, but the more often we do something, the more often we replicate something, the more sure we can be of its results. Psychology is actually experiencing something of a conundrum these days, as classic psychological experiments that we're going to talk about in this class, and you'll see throughout any psychology classes that you take, are not being replicated. And when people attempt to replicate them, the results are not always consistent with the original findings. So there's sometimes what's called the replication crisis in psychology, because we haven't always been very good at attempting to replicate big findings before, announcing them as true, right? So replication is a key step here. Right? So when we think about lumosity, and we think about how we can apply critical thinking to it, particularly the realm of science, we need to come up with some hypotheses that can be falsifiable, that can be proven wrong, that make specific testable predictions. Then we need to go out there and we need to test them, and we need to see what they apply to. So if lumosity says it can help our memory, right, we need to come up with a specific test hypothesis. It says Group A, who uses lumosity, should have a better memory after completing the course than Group B that does nothing. Right? That's a specific testable prediction, and it can be proven wrong, right? If Group A doesn't have better memory, the one who did the lumosity, than the group that did not, then we've proven that hypothesis wrong. It is a falsifiable idea. And sure enough, we can apply this methodology to the claims made, and we can take a look at the results. In fact, let's look now.
Tonight, one of the leading companies in a billion-dollar business for so-called brain training has been fined by the federal government to settle charges of misleading advertising. Lumosity had claimed its online games and apps could improve cognitive ability, even ward off Alzheimer's disease. But as NBC's Tom Costello reports, the company must now offer refunds.
The commercials promised life-changing results.
It's like a personal trainer for your brain, improving your performance with the science of neuroplasticity.
For as little as $15 a month, Lumosity offered dozens of games and claimed that by playing them several times a week, a user could boost his or her performance at work or school, improve ADHD, even keep Alzheimer's at bay. 65-year-old Wes Henson bought a subscription several years ago.
I don't know if I'm losing my memory or not, but I want to improve my memory.
But the Federal Trade Commission fined the company $50 million for deceptive ads, then reduced it to $2 million because Lumosity couldn't afford it.
I can tell a big difference. Decisions come quicker, I'm more productive.
Some of the best testimonials in exchange for awards, as the company played on the fears of an aging population.
But there just isn't evidence that any of that will translate into any benefits in a real-world setting.
That was also the conclusion of more than 70 prominent researchers who in 2014 issued a statement that there is no compelling scientific evidence that brain games can reduce cognitive decline.
I always tell patients to, save the $300, and spend time, an hour or 2 hours playing Legos, with their grandkids, which is much more realistic and I think meaningful cognitive exercise.
Today, Lumosity told NBC News it has made strong contributions to the scientific community, and the $2 million government fine is a reflection of marketing language that has been discontinued. While Lumosity customers can cancel their subscriptions and apply for a refund, researchers do say it's important for senior citizens to remain mentally active, interact with others, exercise, and do puzzles. But there's no guarantee that will keep Alzheimer's at bay.